Okay, just a quick recap of what we did in the previous class. So essentially, we saw some motivation of why we are studying convex sets, because this is a class of if your constraints form a convex set and your function is convex, then there are efficient algorithms to solve these convex optimization problems, and we'll see that a little bit later. But before that, we need to understand the geometry of the convex sets, because this also gives us intuition as to how to design algorithms and how to solve convex optimization problems efficiently. We'll see different kinds of convex sets. Each of these corresponds to a different form of a convex optimization problem. And for each of these, we have different algorithms which can solve these problems very efficiently. And we'll see a little bit of that, in at least a peek into that in this particular class. So we started out by defining what a line is and what a line segment is. That's geometrically intuitive, but we also have this formal definition. So given any 2 points, the set of all alpha x1 plus 1 minus alpha x2 forms the line, as long as you take for all alpha in R. Now, if you restrict this to alpha being between 0 and 1, then it gives you the line segment joining x1 and x2, right? And we defined a set to be affine if it contains straight lines. So given any 2 points, the straight line joining the straight line passing these 2 points lies inside the set. Then the set is affine, right? And in particular, any straight line is affine, a singleton is affine, the null set is affine, any vector space is affine. But in particular, every affine set is essentially a shift of a vector space, right? So given any affine set, you can always shift it back so that you take any point within the set, subtract all points within the set from this particular point, that will give you a vector space. That's always a vector space, right? So in particular, if S is a vector, if S is an affine set and C is any point from this set, then S minus C is always going to be a vector subspace. Right? And the dimension of this vector subspace is called the dimension of the affine space. Yes. Okay. So think of it the following way. Let's look at, let's say, R3. Right? What are all the vector spaces that you can think of? So vector spaces could be, at least the non-trivial vector spaces are going to be lines or planes. Right? Planes passing through the origin, lines passing through the origin. Now we want to sort of generalize this notion of the vector space. So take any shift, any line or any plane, not necessarily passing through the origin. These are affine, right? And effectively, the only affine sets are these kinds of sets. So in R3, the only affine sets are lines, planes, of course, all of R3, or singleton points, or the null set. Right? So that's how you should think of an affine set. It's like a vector space, or if you want to think about it geometrically, these are effectively hyperplanes. Not just hyperplanes, but they could be slightly more general. Think of them as planes, but not necessarily passing through the origin. Okay. In fact, we'll define a hyperplane a little more formally. They'll be a little bit different. But so, for example, in R3, a line is also an affine set. A plane is also an affine set, and these are affine sets of different dimensions in the same ambient space. Okay. All right. So essentially, you can think of an affine set as the solution space to a system of linear equations. There's a one-to-one map between every affine set and some system of linear equations, and the solution space of some set of linear equations. Okay. And given an arbitrary set, need not be affine, the affine hull is essentially the set of all affine combinations of this particular set. So for example, if you take 2 points, then the affine hull of these 2 points is essentially the line passing through these points. Now, if you take, let's say, 3 points, it's going to be the plane which contains these 3 points, and so on. You can generalize this to higher dimensions and more number of points, or arbitrary sets for that matter. So an affine hull is an affine set, right? But so you can think of an affine hull as another set derived from some set. You have an original set which is not affine, which may not be affine. the affine hull is going to be a new set which will be affine and contains the original set. Right? For example, I take 2 points, right? That forms a set. This is not affine. You agree? Just 2 points. Yeah. 2 points. Any 2 points. Just separated in space. Now, what is the affine hull of this particular set? The line passing through these 2 points. Right? So I had one set originally. Now I converted. I transformed this, or I took a new set which contains these 2 points, but is now affine. So another way to think about the affine hull is that it is the smallest affine set which contains your original set. Okay. So you take an arbitrary set. It could be something very weird looking.
So essentially, affine hull is an affine.
Affine hull is an affine set. It is the smallest affine set which contains. So you don't say affine hull in isolation. The affine hull of some set. Right? You have some given set, and you're looking at the affine hull of this particular set. All right. Good. So similarly, we also define these notions of a relative interior and the boundary of a particular set. In particular, this is to handle the problems of dimensionality, because your ambient space could be Rn, but the sets you're looking at could be in a smaller dimension. So for example, you have R3, but let's say that I take a straight line, right, in R3. Now this has a dimension 1, not 3, right? And I still want to be talking about interior points of this particular set, right, which are going to look like open intervals, right, in this particular line, right? So that is why we defined this notion of a relative interior. It is basically, you look at that, you go down to the smaller subspace, which is essentially R1 in this case, if I take a line, and you look at the interior in that particular space. So it's going to be an open set, not in R3, but it's going to be an open set when you restrict yourself to the affine hull of that particular space, of that particular set.
Bn of x epsilon, is that the same thing as the neighborhood of x?
Exactly, it's the neighborhood. It's just the open ball of radius epsilon, which has center x. Yeah. Okay, so geometrically you take a particular set. Let's take an example. Okay, let's take R3. Okay, and for example, let me take just a square, right? I think this was the example that we used last time. Maybe I did. Or fine. So I have R3. This is R3, and my set now, let us suppose, is just this triangular region in the, if I call this the x-axis, the y-axis, and the z-axis. Then this triangular region over here, this is a set. It's a two-dimensional set, right? And it is contained in the xz plane, right? So if I have this particular set, I want to sort of think about, I want a notion of the interior of this particular set. If I view this as a set in R3, then this has interior, it has empty interior, right? Because what is the interior of a particular set? The interior should contain a ball, an open ball, right, or a neighborhood. And a neighborhood in R3 is going to be a three-dimensional ball, whereas this is a two-dimensional object. So I need to somehow think of two-dimensional balls in R3, right? So intuitively speaking, what would be the interior of this triangular set? It would basically be the triangle, but without the boundaries, without the edges of the triangle, right, or the sides of the triangle.
Kind of it.
Correct. It's a wafer. The set itself is a wafer, but the interior of this, or to be more precise, the relative interior of this set would be the same triangular region, but I remove out the edges. Right? It's an open set, right? So it contains everything except the edges. Correct? So how do I formally define this object? I look at the affine hull of this particular set. What will it be? What will the affine hull of this triangle be? Yeah, it's going to be the XZ plane, right? That's the smallest affine set which contains this triangle, correct? And now within this, now I'm down to a two-dimensional space. Now what are balls or neighborhoods in this space? They're circular regions, right? Open circles. And in that case, now I'm down to R2. This is a two-dimension. This has sort of full dimension in R2. And therefore, the relative interior of this set is again now going to be the triangle, but without the edges. Right? So that's the definition of the relative interior of this set. So even though your set may be living in a smaller dimensional subspace, you can still talk about the inside of this particular set, and that is captured by the relative interior. And what is the boundary of this set going to be? Correct. It's only going to be the sides of the triangle, right? With nothing in between. Right? It's just going to be a union of three line segments. Right? And that is basically the set minus the interior, the relative interior. That's the way you should geometrically think about these objects. So again, intuitively, the relative interior is very simple to understand. Right? It's just the inside of your particular set, irrespective of what dimensional space it lies in. Right? And that's very intuitive, very natural to think about, at least for simple examples. Right? And so is the idea of a boundary. Right? So, for example, if I took a cube in R3, what would be the interior? All of the inside of this particular cube. What is the boundary? So basically just the faces, right? All the faces, but with nothing in between. So it's a hollow cube. That's the boundary of this particular set. Now, if I restrict myself to one face of this cube, right? Just one face. What is the relative interior of the face? It's just going to be a square without the boundaries, without the edges, right? And what is going to be the boundary of the face? It's going to be just four edges, right? Four lines, right? So the boundary of the cube itself is the union of the faces. The boundary of the face is just the edges of that particular face. Right? So now we can talk about the inside or the interior, the relative interior, and the boundaries even of smaller of objects in smaller dimensional subspaces. Right? So this is clear.
So if I remember correctly, we defined an open set as a set whose interior is itself, right?
No. Yeah, sure. The interior is itself.
Yeah. So in this three-dimensional space, like
Yes.
if we consider this triangle, and let's
Yes.
say remove the boundary.
You remove the boundary, yes.
So does that mean, like going by the strict definition, does that mean that it's not an open set?
It is not an open set.
So we don't like modify it to mean that
No.
it's
No. Yeah. So by definition, this set is not open. Even the relative interior is not an open set in R3. But the relative interior is an open set when you restrict yourself only to the affine subspace, the affine space, right? Affine hull. Okay. Any questions? All right. So similarly, just as we defined affine combinations, affine hulls, you can also define convex combinations, convex sets, and convex hulls. Right. So just as before, convex combinations are basically combinations of the form alpha 1 x1 plus alpha 2 x2 plus alpha k xk, where the sum of the coefficients is equal to 1. For an affine hull or an affine combination, this restriction that the summation is equal to 1 is previous slide, yes.
One where we will discuss part this open like the triangles. Yeah.
This was right. Yeah. Right.
He was telling that like open sets are defined where like the set is the interior of the set.
Correct.
So what exactly is an open set in like geometrical? Like because
Yeah.
like why is open set changing when we change what do you call it, the substrate element?
Why is the open set changing?
Yeah, like whether the notion of the set being open or not
Yes.
is changing when we are changing new substrates.
Yes. True. Because ultimately the definition of an open set is based on what you define by a neighborhood. Correct? What is a neighborhood? A neighborhood is essentially an open ball. Right? In R3, what is an open ball? It's a sphere. In R2, what is it? It's a circular region. Right? So typically an open set should essentially contain open balls within it. Right? But on the other hand, since you're looking at sets which have smaller dimension, these are not going to contain open balls. You can't pack in spheres inside this particular set. So this is not an open set. But when you go down to a smaller dimension, you can think of the relative interior as an open set within that particular affine hub. Correct. So recall that an affine set was one, which contains straight lines, right? Or in other words, an affine combination is a linear combination of vectors such that the sum of the coefficients is equal to 1. If we add the additional restriction that the coefficients should sum to 1, then that gives you a convex combination. In other words, an affine combination, or the set of all affine combinations, is going to give you a straight line, affine combination of 2 points. Right? A convex combination is essentially a line segment. A convex combination is basically a convex combination of 2 points is basically any point which lies on the line segment between these 2 points. Right? And the set is convex if it's closed under convex combinations. Basically, you take any two points within the set, the line segment joining these 2 points should also be in the set. So at least pictorially, for example, if I draw a set like this, is this going to be convex? No, right? Because for example, I can pick this point and this point, the line segment joining these 2 points is not fully contained within this particular set. Right? So if you take a circular region, is it going to be convex? It is. Take a triangle, is it convex? What about a square? Right? It is going to be. A cube in 3 dimensions, that's also going to be convex. Right? Okay, so that was where we sort of stopped. Yeah.
In this case, if we have kind of a bowl shape in 2D, that's not convex.
A what shape?
A bowl shape kind of thing.
In
Like for example, a parabola in 2D.
Okay, just the parabola itself.
Yes.
The parabola itself is not going to be convex, right? But for example, the entire set which contains the region above the parabola, that is going to be convex. Similarly, in 3D, if you just take a bowl, it is not convex. Right? If you just look at it as a 2-dimensional surface in some sense. Right? But on the other hand, if you look at all the space contained above the bowl, that is going to be a convex. All right. So now let's define a new object, which is a cone. So geometrically, you know what at least intuitively, you know what a cone should look like, right? It has some kind of a tip and it sort of spreads out, right? And we'll formally define a cone in the following way. C is a cone if, suppose that I take any point in C, then alpha x is in C for all alpha greater than or equal to 0. Right? So take any point in this set, and I look at sort of the ray shooting out of the origin and passing through this particular point. Okay, so I have R2. I take any point. Let's call this point X. So what is the set of all alpha X for alpha greater than or equal to 0 going to look like? It's basically this straight line originating from 0 and passing through. Passing through this. It goes all the way up to infinity, but only in one direction. Right? Not the other way around. Remember, I'm taking alpha to be greater than or equal to 0. Only greater than or equal to 0. Okay? So this is, so a set is a cone if no matter which point you pick in the set, all these rays are also going to be contained within this set. Right? So pictorially, what would a cone look like if we just go by this definition? Okay, can you give me an example of a cone? Okay, yep. So basically, this, if you look at the function mod x, it's going to look something like this. So what is this set? How would you define this set?
The boundary of
Okay, so that's certainly the set of all x. You can think of it as set of all x comma mod x greater than or equal to 0. But this essentially just contains two lines, right? But what if I take the set of all xy such that y is greater than or equal to mod x? What does that look like? Basically this entire region, right? And that, well, at least visually, that's what a cone would look like. So if you take, let's say, yeah,
X comma mod x equal to 0 is just the grade.
which,
X comma mod x when x
correct.
greater than
Oh, sorry, x greater than or equal to 0, I should have said x in R. Yeah. So if I take just x greater than or equal to 0, it's going to be just this straight line. For x in R, it's going to be a union of these two straight lines. If I take this set, then it's going to be the entire region in between these. Right? Any questions?
why do we constrain ourselves to like just cones at the origin? Like, why do we also possible to like shifted cones?
You could, but for now, where this is going to be a definition of a cone. It's always going to start out. The tip is always going to be at the origin. So that's
You can switch the greater than with less than equal to the
which one?
y is less than equal to mod x.
Y is less than or equal to mod x. Good question. So is that a cone? So basically this entire region below. Does it satisfy the properties of a cone? You take any point, is the ray passing through it contained within this set? Does everyone agree? How many of you agree? Yes, this is a cone. How many of you say no, it's not a cone? Okay, so for people who say it's not a cone, why not? Not x greater than or equal to alpha greater than or equal to. And okay, you take any point here. take this point over here. Is the ray from the origin passing through this point contained in this set? Is it? It is, right? Yeah.
If we take some point in the fourth column,
You take some point in the fourth quadrant, okay?
to the origin and then extend it. That
You're not allowed to extend it, right? That's the whole point. Right? So that's what it does not contain the entire straight line passing through this particular point and the origin, right? So, for example, if your point is in the fourth quadrant, then you're considering a line which is purely within the fourth quadrant. It doesn't extend to any of the other quadrants. Right? That's my definition of a ray. It starts from the origin and it passes through. Right? So this is in fact a cone. Right? In fact, so are these two sets convex? Okay, so firstly, let's do it step by step. Is this set convex? Yes, everyone agrees that this is a convex set. Is this set convex?
No.
It is not, right? So it's an example of a cone which is not convex. What about if I take the union of two cones? Okay, I have one cone which looks something like this, and another cone which looks something like this. Is the okay? It's not convex. That's fine. Is it a cone?
Yes.
It is a cone, right? Is everyone convinced? Right? So basically, unions of two cones is also a cone, but cones need not be convex. Right? So this sort of generalizes what you, at least what you intuitively think about as a cone. If you tilt what 90 degrees? Okay. No, right? No matter how you, these sort of cones are separated, right? So if you're tilting everything together. It's still going to be non-convex because there's sort of this gap between these two. If I take any point from this cone and any point from the other cone, the straight line joining these two is never going to be inside. Which exactly, you're rotating both together. You're rotating both cones by the same angle.
Does that mean that any closed shape containing the origin, or I mean that any shape, any boundary that contains the origin, any area containing the origin is a cone?
Take any bounded set.
It doesn't have to be bounded, right? So again,
No, that's what. If it is bounded, is it a cone?
it can be, right? So for example, if you have for example, you take a circle that's centered at the origin.
Okay, is it a cone?
Yeah, so if we take any point that's inside, so we take that area of the area inside the circle.
Okay.
Any point inside that will yes, it will be a cone, right? Okay, no, no.
For all alpha greater than 0, not between 0 and 1, right? So a cone is necessarily an unbounded set. Unless, of course, it's a trivial, the empty set, for example, or just 0. Right? So any non-trivial cone is going to be unbounded. Right? And the reason why these cones are special is because in certain cases, you can solve these conic optimization problems where the constraints are in the form of a cone. You can solve these efficiently. So this is an example of an unbounded constraint.
But semicircle,
Okay.
upper half of the semicircle.
So you mean something like this? Okay, so you mean this set? Is that what you're saying?
Within this.
So basically just this set.
Yeah.
It's not going to be a cone, right? Because you take any point over here, is the entire ray passing through this point contained in the set?
But if you consider a circle with limited radius.
That's all of Rn, right? So that's all of Rn, and that is certainly a valid cone. It is a cone. So for example, R2, all of R2, this forms a cone. In fact, take any vector subspace. Is it a cone? It will be, right? Because it's closed under all linear combinations. Is a subspace convex?
Yes.
It is. Is it affine? Yes, because it's closed under any linear combination. And these are all sort of restrictions, right? You're imposing restrictions on the kind of linear combinations that you're considering. So a vector space satisfies all of these properties. Right? And given an arbitrary set, so we defined an affine hull, a convex hull, and similarly you can define the conic hull as basically the smallest cone which contains these particular sets, this particular set, right? So so what is a conic combination? Yeah.
Say this stuff.
Yes, please.
Like, where does this word hull from?
Hull. Okay, I wouldn't. I'm not sure about the origins of this particular word. But for example, if you take a ship, right? What is the hull of the ship? It's that entire sort of region which encloses the ship in some sense. Correct. So the bottom portion is called a hull. Yeah. Tanks also. Sure. Okay. Which tank are you talking about?
Like
The armored tanks or the tanks containing water? So it's sort of like an enclosure, right, in some sense. So given a particular set or given a set of k points, let's say x1, x2 up to xk, the conic combination, any conic combination is basically a linear combination of the form alpha 1 x1 plus alpha 2 x2 and so on up to alpha k xk, such that each of the alpha i's is greater than or equal to 0. Right? And a conic hull is essentially, it's not the smallest, I should be a little more precise here. It's not necessary, it's not the smallest cone that contains this set, but it's the smallest convex cone which contains this particular set. So a conic hull is basically the set of all conic combinations of points in the set. Right? So let's just take an example. Once again, let's take 2 points. Okay, that's the sort of the simplest example. You have R2. I take 2 points. What would be the smallest cone which contains these 2 points? All right, so basically it would be the 2 rays from the origin passing through these points. So it would be basically these 2 rays. Oh, sorry for my drawing, but right, it would be these 2, just these 2 rays. What would be the set of all conic combinations of these 2 points? It would of course contain these 2 rays, but what else would it contain? The entire region in between these 2, right? So for example, if you take any positive sum like of these 2 points, let me call this point x1 and this is x2. What would x1 plus x2 look like? So x1 plus x2 would be some point over here. x1 plus x2. So if you look at any positive linear combination of these 2 points, that would be a point in this particular region. And the set of all positive linear combinations essentially gives you the conic hull. And if you think about it, this is indeed the smallest convex cone which contains these 2 points.
If 2 points are 180 degrees apart, that they form
Okay.
the same line.
Correct.
Then
Yes.
the convex cone would just be the line joining them.
Exactly. It would just be the line joining, line passing through.
That will also be the convex hull in this case.
That is, no, that's not the convex hull, right? Because the convex hull would only be the line segment joining those 2 points. That would certainly be the affine hull. And it's also the smallest subspace which contains those 2 points. So basically you take x and minus x, right? Those are the 2 points that you're considering. Right? So for example, if I have, let's say, some weird set and another weird looking set over here, the conic hull of this set would be sort of the smallest, of the second set would be the smallest cone which contains this set. It would look something like this. The conic hull of this set would essentially be this cone over here. The conic hull of the union of these 2 sets would be this entire region, right? So the 2 cones plus everything in between them. Right?
So if we take 2 line segments, two lines are intersect at the origin. Then what is the conic hull for them?
So you're taking, okay, let's just take the x-axis and the y-axis.
Yeah.
Okay,
What would be the conic hull in this case? Because
Uh-huh.
there's like 2 possibilities like that.
correct. So what do you think it would be? So x can take any value, y can take any value, and you're looking at positive linear combinations of these.
In this case, it will be R2.
It'll be R2, yes,
But
exactly.
if we take 2 line segments that are not the axis, then there will
Correct.
be 2 cones. There won't be 4 cones. There will just be 2 cones that contain on the point. So in that case,
Uh,
what would be the context? What would be the context? Presenting convex segment.
So, okay, so think about it in this way. So from this, so basically you have 2 straight lines, right? Any 2 lines which don't overlap and pass through the origin. That's the set that you're considering, right?
Yes.
Okay.
So in this case,
Correct.
each of these individually we can define the cones with each of these. But then when we take the union, when we take the convex cone that contains these areas, both these areas,
Mhm.
if you take another convex cone
Okay.
that has to contain these areas, in that case it will by definition not be convex.
No, so that will not be, the union of conic hulls is not a conic hull. So for example, let's just take, so from these 2 sets, let's sort of simplify this. Now, since these 2 lines are non-overlapping, I can construct a basis, right? I can take, let's say, any vector of this particular line, any vector on this particular line. These 2 vectors together form a basis for R2. Now, along with this, since it contains the entire straight line, I have the negative of the first vector and the negative of the second vector, correct? Now, what is the conic combination of these 2 vectors? Yeah, so basically it contains the so what sort of linear combinations do I have? That's what I want to think about. Okay, so I have alpha 1, let me call this v1, let me call this v2, and I also have minus v1 and minus v2. Correct? So I have alpha, so what kind of combinations do I have? I have alpha 1 v1 plus alpha 2 v2 minus alpha 3 v1 minus alpha 4 v2, correct? Where all the alpha I should be greater than or equal to 0. Now with this, can I generate any point in R2? Yes, right? Because effectively this is just alpha 1 minus alpha 3 v1 plus alpha 2 minus alpha 4 v2. Correct? Alpha 1 minus alpha 3 can be any real number. Alpha 2 minus alpha 4 can be any real. So this is essentially a set of all linear combinations. So it's all of R2. Any other questions? Yeah.
You are telling the union of two conicals won't be a conical. Like, the kind of like obvious because like conicals have to be like, let's say the boundary.
Correct.
So like if there are like 2 points, like even in the first example, when like there are 2 separate regions.
Correct.
Like the conicals,
Yeah.
like
It's basically this region.
like two boundaries. Like this.
Correct.
For the other one, it's like 2 boundaries. Like this.
Correct.
So the union of them defines 4 boundaries. So
Correct. But that's not always the case, right? It's potentially possible that the union of conicals is also a conic hull. So
yeah, so if they are, if it happens only if one of the like boundaries intersects with the other, so then overall
Correct.
they're
Yes.
that is the only possible.
Exactly. That's the only possibility. All right. Any other questions? Okay. So let's just again see some quick examples. So what can you say about the empty set? Is it affine? Is it convex? Is it a cone? It satisfies all the properties, right? It is convex, it is affine, and it's a cone. Okay, what about in fact any subspace, any vector subspace? Is it convex? It's convex. Let me- So these are convex, affines, and cones. Subspace is also convex, affine, and a cone. Let me take a line segment. Right, take any 2 points, and basically the line segment joining these 2 points. Is it convex? It's convex. Is it affine? No. It is not affine because it doesn't contain the entire, it's a bounded set and it does not contain the entire straight line joining these 2 points. Is it a cone? Okay. What about a ray, which is basically, how do you define a ray? It's basically some x naught plus alpha times say v for some x naught and v in a ray. So x naught is fixed and I'm taking all possible v in R. I'm taking all possible x naught and v are fixed and I'm taking all alpha greater than or equal to 0. So for a fixed x naught and for a fixed vector v, I'm looking at x naught plus alpha v, which is going to be, what is it going to look like? So I have the x naught vector and I have, let's say, the v vector. What would this ray look like? So it basically starts from x naught, passes through v and extends all the way up to infinity.
It's parallel to the.
Oh, so sorry. I should have maybe written it in a slightly different way. Perhaps I should have said alpha times x naught v minus x naught. That's a better way of representing. Right, so this,
Even the first definition is a ray.
it's array, it is array, yeah, but
Like,
it's sort
it'll
of
just be parallel to the start.
correct. Yeah. So what would v minus x naught be? Essentially, what would be the direction of v minus x naught? It would be this direction, right? And the ray would basically be this. Okay, so now is this convex? It's a convex set. Does everyone agree? It is. So basically, it's not a line segment. It's basically a line which extends all the way up to infinity, but only in one direction. So it is convex. Is it affine? It's not affine. For it to be affine, it would have to extend all the way back to infinity. Is it a cone? Yeah. So it's equal to, it is a cone only if x naught is equal to 0. Sorry? Only if this x0 is equal to the origin. Right? So this is basically a ray. For it to be a cone, the ray has to start from the origin. Right? So no, in general, yes, if x naught is the 0 vector. Right? And can it be an affine set? It can be in a certain special case.
Not it's minus or like
No, it's
When v
a
is x
single.
naught.
When v is equal to x naught. So in that case, it sort of, you don't have a ray anymore. You essentially have just a single point. If x naught is equal to
yes, if we consider x naught to be infinite or minus infinity, in that case also it will be a
what is, no, but it's not a vector, right? Infinity minus infinity. Okay. So we'll now see another sort of special class of affine sets called hyperplanes. So basically, so recall there are different ways of thinking about an affine set, and one way is that it's the solution space for some system of linear equations, right? And we'll define a hyperplane H as the set of all x such that A transpose x is equal to B for some. So this is the hyperplane defined by the vectors A in Rn and B in R. Right? So in particular, this is a hyperplane. It's an affine set. And what is going to be the dimension of this affine set? It's going to be n minus 1, right? So this is an affine set of dimension n minus 1. So for example, in R2, what is a hyperplane? It's essentially a straight line, right? And what does the hyperplane do? It sort of partitions the space into two regions, right? One above the hyperplane and the other below the hyperplane. And these are what we'll call half spaces. Yeah.
We know that a hyperplane has the dimension of n minus 1 in any dimensional space.
Correct.
Mathematically, how do we show that the dimension is n minus 1?
The dimension is n minus 1. how many solutions does, so it's a system of linear equations. How many solutions can there be for this? What can you say about the solution space for this system of linear equations? Can it be inconsistent? How? Which, okay, A is 0, B is non-zero. So let's assume that they're all not, at least A is a non-zero vector. Okay, maybe I should have said that this is a non-zero vector. Okay, let's avoid that particular situation. And yeah, if both A and B are 0, then it's basically the dimension is n because it contains all of Rn. But if A is a non-zero vector, then can it be inconsistent? It cannot, right? There's only one equation anyhow, so it can't contradict with any other equation. Okay, so it's just one. So, and therefore, what would be the solution space? What would be the dimension of the solution space?
Should be one dimension.
Why? Okay, so firstly, let's look at A transpose X equal to B. There is at least one solution. You agree? There's at least one solution. Let's call that X star. Okay, so you can write A transpose X as A transpose X star because B is equal to A transpose X star. There's at least one solution. That you agree, right?
So the null space is n minus 1 dimension.
Exactly. Yeah. So it's A transpose into X minus, yeah, sure, X minus X star. So it's the null space has dimension n minus 1 equal to 0. So it has dimension n minus 1. So it's going to be an n minus 1 dimensional set, and essentially the set of all X such that A transpose X greater than or equal to B. I can construct another set X such that A transpose X is less than or equal to B. And these two are called half spaces. And these are basically the kind of sets that you get by imposing linear constraints on your system. Yeah.
The solution to the intersection.
The solution to the intersection. Fine. It's the intersection of these two half spaces. Right. But at least the interior of these two half spaces are going to be non-intersecting.
Is there any, as per convention, I understand we have included the hyperplane in both the spaces.
Correct.
Is there any advantage
of doing this? Yeah, so that's precisely because these are, so what are these? These are basically going to be constraints. Each of this is going to be one linear constraint, right? And we are only looking at inequality constraints of the form greater than or equal to, because we want our sets to be closed. So basically all the sets that we have considered so far, right? The way we've defined a convex set, the way we defined an affine set or a cone, these are all closed sets. Right? These are all closed sets. And similarly, the reason why we are defining hyperplanes in this particular form is that these are closed sets. So typically, whenever we do convex optimization, we want our set to be closed, or the set which defines the constraints to be closed, because then we are guaranteed, at least if it is also bounded, then it's guaranteed to have a solution. right? Yeah. Any questions?
Geometrically, hyperplane looks like a plane if you take 3D.
Correct. So in 2D, a hyperplane is basically a straight line, right? In 3D, a hyperplane is going to be a plane, right? But in R3, you can have other affine sets. So hyperplane is always a plane, a conventional plane, but an affine set could either be a plane or it can also be a straight line, right? That's also a valid affine set. But in R3, a straight line is never an affine set. It's always a plane. And if you go to R4, which we can't visualize, it's going to be a three-dimensional object. Right? Great. So now, essentially, what we have is,
There is a why in that word hyper is added.
because it generalizes a plane, right? If you go to R4, for example, so in R4, it's a hyperplane is basically a three-dimensional object. And that's why you add the word hyper, because it's true not just for 2 in R3. It's you also the same definition carries forward to n-dimensional space. So, for example, the word hypersphere is sometimes used instead of a conventional sphere. So in R4, the n-dimensional, whatever, in Rn, the n-dimensional ball is called an n-dimensional hypersphere. Again, sometimes it depends on what convention you follow. At times, there's mild abuse of the words. There are some places where people also refer to affine sets as hyperplanes. So, for example, even the straight line in R3 is sometimes called a hyperplane. But really, again, we're following one particular convention. These are, and we're calling only n-1 dimensional objects as hyperplanes.
Actually, what is the difference between plane and hyperplane? Is plane fixed to be two-dimensional?
Plane is fixed to be 2 dimensions. Typically, that's the convention that people follow. Okay, so let's try to visualize what happens. Suppose I give you a bunch of linear constraints. Okay, so I have a1 x less than or equal to b1, a2 x less than or equal to b2, ak x less than or equal to bk, right? Sorry, a1, a2, so a1 transpose x less than or equal to b1, a2 transpose x less than or equal to b2, ak transpose x less than or equal to bk, where each ai is in Rn and each bi is a real value. All right? What would this set look like? There are different scenarios that can arise, right? So let's look at R2 and take one such constraint. So in R2, what does a1 transpose x less than or equal to b1 look like? You draw a line. It's going to be one side of a line, maybe this side, depending on what a1 is and b1 is. It's this particular region. I impose another constraint. Now if these two vectors are sort of linearly independent, then I'm going to get another constraint, right? Now this could be either to the right or to the left. So maybe this second constraint gives me some region to the left. So if you impose these two constraints simultaneously, then basically what I would get would be this region, right? This conical shaped region. Now impose a third constraint. Again, perhaps it could be something like this, right? So now So basically, if I impose all these three constraints, then I would get some kind of a region like this, right? So this, again, if I take just three constraints, then potentially I could get an unbounded set. But I could potentially also get a bounded set. So for example, if some hyperplane defines, if I take another hyperplane and take this particular half space, then the intersection could potentially be an unbounded, a bounded set. Right? And sets of this form basically obtained by taking the intersection of half spaces. Then of course they're convex. Does everyone agree? So it's convex, and such sets are what are called polyhedra. Right? Now there's some confusion or inconsistency in the notation. Sometimes people use the term polyhedra, sometimes the term polytope, and people use this for different things. Essentially, they correspond to the intersection of a bunch of half spaces, but the only inconsistency is whether it has to be a bounded set or it could potentially be an unbounded set. So if I take intersection of half spaces, it could be an unbounded set, right? Potentially, just take one constraint that gives you an unbounded set. But potentially some of them could give you a bounded set. So sometimes bounded sets are called polytopes, and potentially unbounded sets are called polyhedra. The more general form is called a polyhedra. But some people also prefer to use the reverse. They use the word polyhedra for bounded polytopes, and so on. Yes.
Like, do we name the half spaces like according to whether they are
Above or below?
above or below the origin?
You can't really, I mean, just by changing the sign of B, you get the other way around. So really, just by changing signs, you can get something totally different. So typically, you just consider one of the half spaces. One inequality basically gives you a half space. That's how you precisely define that particular half space. Okay, and these are particularly important for certain kinds of optimization problems. So in particular, again, let's try to develop some intuition. So what is a bounded polyhedron or polytope going to look like? Let's just take 2 dimensions. Okay, it's going to be some polygon, right? So let's.
So what dimensions are we going to put polyhedron and polytope?
So I'll explicitly specify whether it's bounded or not. Okay, to avoid any sort of confusion, right? So I'll mostly use the term polytope for bounded polyhedra, but I'll say whether it's going to be a bounded set or not. Okay. So let's take a bounded polyhedron in R2. So I'm just looking at x1, x2. I look at the x1, x2 plane. This is going to be some polygonal region, some convex polygonal region. It's not any polygon. It's always going to be a convex polygon. Okay. Now let's look at a function defined in this particular region. Okay. Suppose I have some kind of an optimization problem. So I have some function to, let's say, minimize, and my constraints are in the form of linear constraints. So as long as I have linear constraints, my constraint set is going to be a polyhedron. Okay. So for example, if it's in R2, if I have two variables, then my constraint set is going to be some polygonal region, convex polygonal region. Now in particular, if my function itself is linear, right? For example, let's say my objective function f of x1 separately, f of x1 x2 is say alpha x1 plus beta x2 subject to a bunch of inequality, some linear constraints.
Again, explain the set.
Okay, so I have two variables. I have a function of two variables. Okay, now there are two things, right? One, what is my objective function, and what are my constraints? If my constraints are linear, then my constraint set, basically the region I want to optimize over, is going to be a polyhedron. And let's suppose that the polyhedron is bounded. It's going to be this particular region. Now in any bounded set, as long as I have a convex function, there are sort of two cases. The minimum is some point in the interior of this particular constraint set, and the other case is when it's on the boundary, right? But suppose that my objective function is linear. Can the minimum ever be achieved in the interior of the set? Irrespective of what the constraints are, can the minimum of a linear function be achieved in the interior of any constraint set, or the relative interior of any constraint set? No. Why?
Because you cannot just move in one direction to make them.
Correct. So as long as you're in the interior, in the inside of any particular set, there will always be a direction in which the function is less than what you are presently, right? It's a linear function, correct? So you can always move in a direction no matter which point you take, right? Again, it's a linear function, so there's always a direction where you can go more, where the function value is less than where you are presently.
There may also be a case where there are multiple minima, right? For example, if one is parallel to an axis.
Correct. So there's one case where there's always the sort of trivial case where the function is a constant. That's the only case where this will arise. Well, okay, it could, along a certain axis, it could be a constant. There is that possibility as well. So that's the only case where the minimum is going to be sort of in the interior, right? But no matter what happens, the minimum is always achieved at some boundary point, even in this case, right? So as long as you have a linear function, the minimum is always achieved at a boundary point. Which
you was talking
correct.
about.
So suppose that the function is a constant. The minimum is of course achieved at an interior point, but the same minimum is also achieved at a boundary point. That's the only point that I'm trying to make. Right?
We are saying that there won't be any minimum, but again, there is minimum.
So the minimum subject to these constraints. Right? So you're trying to find the minimum within this particular set. Correct? But if you're in the inside of this particular set, there's always a direction in which you can move so that you can go even lesser. So let's just take, maybe to visualize, let us just take a function of r. Okay, simple case. So what is a linear function? It's some straight. This is f of x, and this is x. And my constraint is what? It's basically corresponds to some interval. So maybe I'm trying to minimize this function over this particular interval. So now in this case, where is the point? Can the minimum point be inside this particular interval? that is in the interior of this interval? No, right? It's always at one edge. No matter what linear function you take, the minimum will always be achieved at one of these two boundary points. Correct? And that holds true in higher dimensions as well. For linear functions, specifically for linear functions. And in fact, if you think about it a little bit, if your constraints form a polyhedron and it's bounded, right? A bounded polyhedron, a bounded non-empty polyhedron, then of course the minimum as before, it will lie on the boundary, but there's something more that you can say. It's not just, there could be multiple minima points of minima, of course, but the minimum will be achieved at some vertex, not just an edge.
Because again, if you move in that direction.
Yes, you can always move in some direction towards a vertex. So let's think about it a little bit. Suppose that the minimum is achieved at some point on an edge, right? Then it necessarily implies one of, if the function is, if this is a point of minimum, right, then all the points along this edge should also be points of minimum. Again, all of this I'm just giving intuition at this point. I'm not making any formal statements, but that's something that you can prove. There can be two cases. So if you take any point on the edge, either you can move along the edge where the function value decreases, or the function value remains the same along the edge. If the function value remains along the edge, then you can always move towards the vertex, and that vertex is going to be a point of minimum. Right? Again, this is just intuition. And in fact, some of the early solvers for solving for minimizing linear functions subject to linear constraints, they use basically these ideas. You start from one of the vertices, pick any vertex you want, and then you keep moving along the edge till you hit a point of the minimum. If you hit one particular vertex and you see that along any of the other edges the function value is not decreasing anymore, then you stop at that particular point. Right? It's sometimes called this was called the simplex algorithm, and it was one of the earliest efficient algorithms, so-called efficient algorithms, to solve this particular problem. I mean, things have come a long way after that, of course. There are better solvers today. Right? So in fact, let's just see one particular application. Yeah. Which one? Correct. Correct. The minimum will still occur on the boundary, irrespective of what the constraints are. That is always true. But if the constraints are linear, then it's not just any point on the boundary. The minimum will occur at some vertex of this particular polygon. So in fact, you don't have to look. Your search space now becomes even smaller, right? Because it's a finite set, right? As long as it is bounded, of course. That's the only thing. So let's maybe just introduce one particular application of a so-called linear program. So a convex optimization problem is a linear program if the function is linear and all the constraints are also linear inequality constraints. Sorry? For non-convex sets. Yeah. Correct. Yes. It's closed in couple, so it will be on the boundary. So even if it's not, if the set is non-convex but your function is linear, the minimum will always be achieved at some point on the boundary, right? As long as it is a bounded set.
We have monotonous function.
Okay.
Monotonic function.
Yes. Yeah.
Generalized.
And that's really the reason why the minimum is achieved at the boundary pair, right? Because yeah, again, monotone, you'll have to be a little more precise because it depends on what direction you're moving in.
Minimum or max.
Correct.
So, a monotonic function, it may not be a vertex, but it will always be an edge, right?
Correct. Yeah. So in general, if it's a general convex function, which is fine, where the unconstrained minimum is not inside this set, the minimum will be some point on the boundary. It could potentially be even on the edge, but only for linear functions, you are guaranteed to find a vertex which achieves the minimum. So a linear program is basically, you have f of x equal to some A transpose x, subject to the constraints A1 transpose x less than or equal to B1, A2 transpose x less than or equal to B2, and so on. And potentially some equality constraints as well. You could model these as inequality constraints, but we'll write them out separately. So C1 transpose x equal to D1, C2 transpose x equal to D2, and so on. Okay. I guess we're out of time, but in the next class, we'll see an application of linear programming, and we'll see how to solve this particular linear program, not closed form.